So what we do next is that we are going to learn a theorem that uses eigenvalues and eigenvectors to compute or to come up with the general solution of such system. So we write theorem. Suppose, so we're going to say, okay, let P be an n by n matrix. Okay, so if P has n distinct eigenvalues, let's say these eigenvalues are called lambda 1, lambda 2, all the way to lambda n, then there exist n linearly independent eigenvectors maybe I should have written here there exists n linearly independent corresponding eigenvectors. I'm going to call them v sub 1, v sub 2, all the way through v sub n. So when I say linear, that they are corresponding eigenvectors, what I mean is, in other words, when we multiply p times v sub k, this equals lambda k v sub k for all values of k. That's what it means to be a vector that is the so-called eigenvector corresponding to a specific value that we call the eigenvalue. So if you have that combination of that value and that vector, is because they satisfy this equation, which on one side has a matrix vector multiplication and the other side has a scalar vector multiplication, and they match. So lambda 1 is paired with v1, lambda 2 is paired with v2, and so on. That's what we mean in this theorem. So we have a matrix P. If this matrix has n eigenvalues which are not repeated, they are distinct n eigenvalues, then there are n corresponding eigenvectors that are linearly independent such that the general solution to the system dx dt equals px is given by a linear combination of those linearly independent eigenvectors. It's given by something that looks like ck e to the lambda k t times vk, and we're going to take the summation here from k equals 1 through n, and this linear combination is exactly what we're going to say. This is exactly equals to x, in fact x of t. So this is a general solution. That means that those coefficients C1, C2, C3, C4, all the way through Cn, they are coefficients to be determined by initial conditions. Right? This is the general solution. The important thing here is that the values, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, all those lambda values are now exponentiated. They are raised, they are passed on as the argument of the exponential function. So here is e exponential function of lambda multiplied by t. Remember, we are looking for values x1 of t, x2 of t, x3 of t, and so on. Right? So this expression has to be a function of t. And so here is lambda with argument, exponential with argument lambda times t, t being the variable, that's the independent variable, the definition of this differential equation problem. And then, but this is the exponential with this argument. This part is a scalar. This is a number for each value of t. That scalar is multiplied by coefficient c of k, which is also scalar. So that product is a number. So the product of these two things is a scalar. And that scalar is multiplying this vector v sub k. That would be a column vector. So writing it in this notation, we're saying that that's a summation of the v sub k, is a summation of the eigenvectors with some specific coefficients. And the coefficients here are c times e to the lambda times t. In other words, that summation of the eigenvectors is a linear combination of the eigenvectors. So if we know the matrix P, which defines this system of linear ordinary differential equations, if we know that matrix P, then we proceed to know the eigenvalues of that matrix, and then the eigenvectors corresponding to those eigenvalues, and then we can write down the solution of that system. So let's go back to what we did last time. Let's go back to what we did last time. Let's say we have derivative of x1 given by ax1, derivative of x2 given by bx2 plus x3, derivative of x3 given by ai x3. So we have three differential equations, for one for each state variable, x1, x2, and x3. So the first thing we're going to do is we're going to rewrite this in matrix vector notation. Okay, so the first equation we can think of 0 x2 plus 0 x3. In the second equation, we can think of 0 x1 plus bx2 plus 1 x3. And in the last equation, we can think of 0 x1 plus 0 x2. Which means that we can write this as the first row is A, 0, 0. The second row is going to be 0, B, 1. And the last row will be 0, 0, A, I. That matrix, 3 by 3, is multiplying a vector with the state variables, which is a vector containing x1, x2, and x3. And on the left-hand side, you can write this as the derivative operator, d dt, acting on the vector x1, x2, and x3. Okay, so this 3 by 3 matrix is the matrix we worked with last time, right? We had computed the eigenvalues, and we had also computed the eigenvectors, and then we had verified which vector goes with which value and so on. So based on your notes from last time, let's find the notes from the previous lecture. So what would be the eigenvalues of this matrix? What are the eigenvalues of this matrix? A, B, and basically the entries, right? The entries of the diagonal, the 1, 1 entry, the 2, 2 entry, and the 3, 3 entry. Those are the eigenvalues. This matrix is triangular. And because of properties, or because of the definition of determinant, properties of determinants, then we had found that eigenvalues are the entries that appear on the diagonal of this matrix. Now, we did a little additional work, and we had established which vector goes with which eigenvalue. So let's review that. So we have, and I'm going to call them lambda 1, V1, lambda 2, V2, and lambda 3, V3. So we have lambda 1 equals, say, A, and V1, we found that the vector that goes with that eigenvalue is 1, 0, 0. Also, lambda 2, let's say that lambda 2 is B, we had that the vector that goes with this eigenvalue is 0, 1, 0. Then lambda 3 is A times I, and we're going to write that V sub 3 is 0, 1, AI minus B. Right, that was the last thing we did. We had verified, we multiplied the vector, we had multiplied the vector by the matrix, and we verified that that scalar times that vector is equal to that product. So that's what we've done. So now we normally, I would tell you to, at this step, do some verification. Verify. Right? Which basically is that. Verify that P times V1 equals lambda 1 V1. P times V2 is lambda 2 V2. And P times V3 is lambda 3 V3. That's what verification would mean here. But we had previously done that. Are we all on the same page? So what we're going to do next is to raise the exponential to the power lambda 1 times t. So consider e to the lambda 1t, that would be e to the at. Not much to do there. Also, the exponential e to the lambda 2t would be e to the bt. And then e to the lambda 3t would be e to the, I'm going to write that as ia times t. AI or IA is the same. So which means that using that formula, what is it called? The what formula? When you have exponential of something I, remember here I, this I here means square root of -1, right? That's what we mean in that I, in that definition of that matrix. The I involved in that matrix in this example. So Euler's formula tells us that we can write this as cosine of AT plus I sine of AT. It's an application of Euler's formula. So, let's see. This is the matrix we're calling the matrix P. We had previously computed the eigenvalues being A, B, and AI, the entries on the diagonals. The calculation of eigenvectors is non-trivial. We had, you have two ways. You could do that by hand by computing a basis of the null space of a matrix. You could do that by using a computer algebra system. Sage math would be a good thing to apply here. And more importantly, if you're given the eigenvectors, you have to verify which vector goes with which value, and that relies on products that are matrix vector products and scalar vector products, and that's what we've done so far. So what we do next is to evaluate the exponential. We exponentiate lambda 1t, lambda 2t, lambda 3t, the first two. Lambda 1 is A, lambda 2 is B. Those are just nothing else to do. But lambda 3 here is a complex number with zero real part. The imaginary part of lambda 3 is given by the number A, but its real part is 0, right? And so by evaluating e to the lambda 3t, we can do an extra step where we are using Euler's formula. So what we'd like to do next is that we'd like to compute e to the lambda 1t times v1. Okay, so this would be e to the at times v1, and v1 is 1, 0, 0. So we're looking here at e at 0, 0. Also, we're going to compute e to the lambda 2t v times v2. Excuse me. So e to the lambda 2t is b times t, and v sub 2 is vector 0, 1, 0, and this becomes 0 e to the bt 0. And then the last scalar vector multiplication, e to the lambda 3 t times v sub 3. So that's what we had established, that e to the lambda 3t is cosine plus I sine because of Euler's equation. So this involves cosine at plus I sine at, and this is multiplying the vector 0, 1, ai minus b. So this is a scalar. It has non-zero real part, non-zero imaginary part, but it's a scalar. That scalar is multiplying each of the entries of this vector. So the first entry is 0. The second entry, multiplying that by 1, is precisely cosine of at plus I sine of at. And the last entry is a little more involved because, let's say, this would be, for example, this would be cosine at times ai minus cosine at times b plus I, so here we have an I square a sine of at, and then we have a minus I sine of at times b. So those are the last entry of that vector is a little more involved, right? So the first entry is 0, the second entry is cos plus I sine, and the last entry requires to do a little more of simplification. Let's see if we can simplify a little bit. So first entry, second entry, cos sine plus I sine, and the last entry, after doing some, so the I squared is -1, so we can write this as minus a sine at minus b cosine AT plus, and we can factor I, can write this as I times A cosine AT plus, minus actually, minus B sine AT. Right? So this is a vector. Looks kind of convoluted, but this is the vector obtained by multiplying E lambda 3t times the eigenvector corresponding to lambda 3. So that's the vector that we obtain here. We wanted this because ultimately we would like to write down the general solution of the system of ordinary differential equations. The linear system of ordinary differential equations is linear on x1, x2, and x3. But to write that solution, we have to write a linear combination of the exponentials with the lambdas multiplying the eigenvectors, right? So what we've done here is kind of going step by step, computing the exponentiate, the eigenvalues, and then you multiply each of those exponentials by the corresponding eigenvector, and now we're going to write them, we're going to add them up, okay? So the general solution of dx dt equals p of x is, this general solution is of the form c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2 plus c3 e to the lambda 3t v3. That's what we want, right? So there is an additional coefficients here, the c1, c2, and c3 we have to take care of it. So that means that x of t is looking like c1 times a vector c2 times another vector plus, here's where we're going to need more room, c3 times another vector. So we had the first vector we found was e to the at 0, 0. The second vector is 0, e to the bt 0, and the last vector is 0 cosine at plus I sine at right. So this is the last calculation we did here. So we have minus a sine minus b cosine minus a sine minus b cosine plus I times a cosine minus b sine. So bringing all, this is a summation. This is a linear combination of three vectors. So we have to multiply c1 times the first vector, c2 times the second vector, and then so we bring this together. This becomes vector with entries c1 e to the at, c2 see, c2 times e to the bt plus c3 times cosine. So here we have c2 e to the bt plus c3 times cosine at plus I sine at. And the last entry is c3 minus a sine minus b cosine plus I So in other words, this here is that vector we're calling x, right? And so remember that vector x is the vector with entries x1 of t, x2 of t, and x3 of t. So what this equal sign is telling us is that here, this expression, c1 e to the at is x1. The second expression, c2 e to the bt plus c3 times cos plus I sine, that would be x2. And the last entry, c3 times quantity, and then there's an expression there, that would be considered the state variable that we're calling x3. So that x1, x2, and x3, those functions of time are the solutions of this system. Remember, this is the original system of differential equations that we first wrote in matrix vector notation, and then we proceeded to apply the theorem. Sometimes this is referred to as the eigenvalue method. This theorem tells us that we can express the solution. It's a linear combination of the eigenvectors where the coefficients in that linear combination involve exponentials of the eigenvalues. Right? And that's what we did in this example.